Hello everyone, this is going to be our test review for exam 3 or exam 3 review. Okay, so I think we're going to have a total of 11 pages. I'll try to limit it to 30 to 40 minutes if I can. Okay, so 6.2, the top one here, the 6.2, you're going to have to be comfortable finding an area under the curve of a normal standard normal distribution. The standard normal distribution just means that I'm dealing with all standardized values. Okay, how many standard deviations I'm away. So the first one says, what's the probability that I get a z-score between 2.12, which is over here, and 3.08. Okay, so it's a between. So we have to go ahead and shade this area in. I shade this area in here. That's the area I'm trying to find. Okay, so what this looks like as notation is the probability that 2.12 is less than z. You need to be comfortable with it either way. Okay, and here I'm going to show you two different ways to do this, and one would be in StatCrunch. So let's pull my StatCrunch over. Okay, so we're on a z distribution. We're going to go stat, calculators, normal. Z is normal. Okay, let's pull up my normal distribution, and what I want to do is make this shaded region look like this region, but we can't do this in this case. So in this case, you have a few options. And one of those options is to let me see if I could keep this on top. Nope. Okay, this is going to disappear. That's okay. Okay, so one of these options is we want to find this value. Okay, we want to find to the left. StatCrunch doesn't give us to the middle. We have to do it different sections. I want to find this, which I'll call B. So we want to find A plus B. Okay, find A plus B and add it, and then do 1 minus that. That's going to give us our answer. Okay, so let's do 2.2 and less than. So stat something happened. Stat calc normal. Now we want to do less than. So we'll get 0, 1. That's our standard mean and standard deviation. And I want to do 2.12. But I want that to be less than. Compute. Okay. So that's the area there. So it's going to be 0.983. 0.983. That's my A. My B, essentially my B is going to be 0 because there's not going to be much area to the right of that. Okay, I didn't have to do that again. Here it is. So I want to go to the right of 3.08, which is 0.001. Now what we do is just sum these up. Okay, 0.984. So my A plus B equals 0.984, but that's the outsides. I want the insides. So the inside's actually going to be 1 minus that. So my answer is going to be 1 minus that. Answer is just that right there. So it's going to be about 1.6%. Sorry. Fix this. 0.016. So about 1.6%. Okay. Okay. So the other thing from 6.2 that I'm going to ask is being able to find being able to find a critical value. In other words, if I give you a z-score, can you give if I give you a percent, can you give me a z-score? So this is the other thing that's not on the review. So this is z of, let's say, 6%. So what we're looking for here is the critical value right here. This z right here. I'm on my normal, so this is z. So I'm looking for this z value right here. That z value. Okay? So I need to just make my StatCrunch look like this. Just make my StatCrunch look like this. So let's go ahead and stat. Go to normal calculator. Go to normal. And never mind, I have it right here. So now if you note, these are the percents over here on the right. So I need to make this percent 6. That's 0.06. I want it to be greater than. So this region should look like this region. So the critical value with 6% over here would be 1.55. So the answer would be 1.55. Okay. Okay, so I wanted to show you how to do this on the TI-83. I did that in class the other night too. Let's go the TI-83 or 84 to find this answer here. It's much easier in this case. Okay, so if I'm trying to find this area from 2.12 to 3.8, all we have to do is go to second vars. We're in a normal distribution. We always use CDF. That's cumulative. That means it's going to accumulate all the shaded region, and we just put in the left and the right. 2.12 comma 3.08. The reason why I don't have to put anything past this is because the calculator is programmed for a mean of 0 and a standard deviation of 1. Okay, so if you round this, you get the same thing. If you round to 3 decimals. Okay, so that's how you do it there. You would just do normal CDF, put in your first bound, put in your second bound. So that's just another way to do it. Okay, now that's 6.2. 6.2 deals with z values. Okay, 6.3 on the other hand, 6.3 deals with x values. Okay, you could always turn your x's into z's and do it over here, but generally, since we have the functions and we have the computing power to do it, we just would rather just work in the x distribution, just using the regular normal distribution, not the standard normal. Okay, so there's some key words here that you always want to look for when you're reading a problem, and one of them is approximately normally distributed, because once you say approximately normally distributed, that allows me to draw this graph right here, which just tells me that most of the data falls around the mean. Okay, so it's 492.91. That's my average price, and the standard deviation is $52.14. So generally, sometimes we can write this notation like this: 492.91 comma 52.41. Okay, so a question I could ask is something like this: if you randomly pick one swing set, what's the probability that it's greater than 500? So this isn't on the review. This is just something that you may be asked. So if you come here, if it's greater than 500, you want to find 500, which is over here. Draw a line up, and we're interested in finding this shaded region down here. Let me just close that up, see if that was the problem. Okay, there we go. I'm interested in finding that shaded region right here, all the way to the end. Okay, so and I'm not in my z's. So this is 500. Well, it does not look good. I'll be there in a sec. 91, and that there is $500. Okay, so in this case, we want to use our StatCrunch. So let's use our StatCrunch, and we're going to go to the same distribution, our normal distribution. And what we want to do is make our mean. Now we just change our mean. So 492.91. Standard deviation of $52.14. Now I want my mean to be greater than 500. So 500 goes there. That's a less than, so I want to change this to a greater than. Make sure everything matches up. This is correct. So the chance is about a 44.5.44, I think it was 6. If I round, that's 9 goes to a 6. Yeah, 446, that's right. Okay, so now the second question actually asks backwards. Okay, this is one of the backwards problems similar to these z's. Okay, so if I have the z, I give you a percent, you can find me a z. Well, if I give you a percent here, if I give you a percent right here, and I tell you this is the bottom 10%, that's the bottom 10%, then I could find this value here, which is an x value, which is an x value. All these are the costs. All these are costs. Okay, so the way we do that is basically the same way we did the other one, but we're just working backwards. Okay, I am working backwards. So to answer this question, what's the least expensive 10%? How much of it? This red area here has to look like this area right here, so it needs to be a less than, and I need to turn this into 10%. Right now it's at 55%. So 10% is 0.1, and let's make sure that's 10%, that's 10%. So the cost would be around $426.09. So let me pull this back in here. So the cost of this would be $420.09. Let me change the color on that. 426.09. Okay, that'd be the cost for the low. Anything this and lower will be in the lowest 10%. Okay, so be really comfortable going both ways on the x's and going both ways on the z's. Okay, next we're going to be going to 6.4. So in the homeworks there were these long problems where you had to, okay, they gave you a p, and then you took a bunch of sample p hats. Okay, sample p hats. There was many of them. There was many. And then what happens is you found this p hat 1, you found p hat 2, you found p hat 3, etc. And then you averaged all p hats. Okay, and what happened, but this is the notation we call it, we averaged the p hats. And if you notice, when we averaged the p hats, it actually equaled this population. It actually equaled the population from the proportion from the population. So if you take the average of all the sample proportions, it actually equals the population proportion. So when that happens, we call p hat and unbiased estimator of p. And what that means is that these are sampling distributions now. So that means that if p is here in the middle, okay, that means that if you take samples, let's say this is your population, say this is your population right here, p, so this is p with the square root of p, 1 minus p, this is your standard deviation. Okay, so if you take samples of size n, what that means, if p hat is an unbiased estimator of p, that means I don't expect, When I sample out of the population, I don't expect all my p-hats to be way down here. This would be a biased estimator. If all my p-hats are all down here, then that means that they're not next to here. Now, if it's unbiased, that means there's no bias. That means that I don't expect them to all fall here. I expect all my p-hats to fall around the p. Can we have one occasion? Can I have an occasional p-hat over here? Yes. Occasionally you can, okay, but not too often. Most of them, if it's unbiased, it's going to fall around here, okay. So it's the same idea. It's the same idea with x bars. Okay, so if you have some population of x bars, okay, I'm interested in mu. The parameter for a population is mu. Okay, with regular, this is the standard deviation. So this is my population, and I start sampling, you're going to get an x bar, and another x bar, and another x bar, and another x bar. If you take the average of all your x bars, we call it mu of x bar. Now, if it's an unbiased estimator, the average of all these x bars, the average of all these x bars should equal the population average. So in this case, x bar is an unbiased estimator, which is the same thing. It's like if I took all these x bars and I graphed them, if I took all these x bars and graphed them, and the mean's always in the middle, the mean of the population, I say, where do I expect all these x bars to fall in my sampling distribution? Now I wouldn't expect them to fall all the way over here. All my x bars won't fall over here. This is an overestimate. If this happens, something happened in your sampling method. If all your x bars fell here, then this would be a bias estimator. Okay, because this x bar is actually overestimating this. Okay, this x bar should be lower. So if it's an unbiased estimator, then we expect all the x bars to fall around here. You may get a few out here once in a while, but most of them are going to fall around here. Okay, so you should have that concept. You should know what this means right here. You should know this statement right here for both of them. Okay, let's move on. 6.5. Now 6.5 is a little extension of what we just did. Now what's important to know is if you take a sample, if a sample is taken and we want to know how likely we are to get the sample, to get the sample mean or proportion, how likely we are to get the sample x bar. Okay, that means that we need to compare it with other x bars. We need to compare it with other sample means. So if that's the case, then I have to have a distribution made up of x bars and not x's. Okay, so we know from the last page, if I take the average of all these x bars, then that's going to be the same mu. So this is normal with this regular standard deviation. But how much of these x bars are going to vary from each other? These x bars are going to vary less from each other. So we did this in class a bunch. So this is the standard mean and standard deviation. Okay, that's the mean and standard deviation of all my x bars. So all these are x bars. These are all possible samples. Now we already know that most of them should fall around the mean, and occasionally we'll get one far away from the mean. Okay. Okay, so let's see if we can answer this question. Okay, so for a sample of 50 new cars, determine the mean and standard deviation for all possible sample means. Well, these are all possible sample means. Okay, so we need to find what we're trying to find in this first part right here. We're doing this one right now. For samples of 50 new car sales in 2007, determine the mean and standard deviation of all possible sample mean prices. Well, these are all possible sample mean prices with n equals to 50. If I took the average of all these x bars, you're going to get mu. They tell us what mu is. So the mean, this is the answer. The mean is 28,200. Okay, that's the mean of all your x bars. What about the standard deviation of all of our x bars? This is the standard deviation of all your x bars. You always have to divide it by the square root of n. Okay, so the standard deviation of all my x bars, which is right here, the standard deviation of all possible sample means, is going to be the original standard deviation, which would be 200 divided by the square root of 50. Okay, so this is the answer for the first problem. The second problem is just exactly what we were doing before. Okay, exactly what we were doing before. You guys got to get comfortable using your StatCrunch. Okay, so what this means is I could work on this one, but I'll just draw a new one. Okay, so the mean is 28,200, and I want to find what's the probability that it'll be 50 cars less than 25,000. So 25,000 somewhere over here. That's 25,000. Okay, that is 25k if you can't read it, and it's less than, so I want to shade less than. Let me change the color. Let me check my time. Oof. Okay, so maybe it might be a little longer. Okay, so now what we have to do is to find this. We have to use our StatCrunch. We pull our StatCrunch out. Okay, and let me pull this out just so I could get my mean and standard deviation. So it's going to be, I'm getting my standard deviation now. So the mean is 28,200, and the standard deviation of all my x bars is 10,200 divided by root 50. Okay, so it's going to be 1, 4, 4, 2, and I'll just round that to 0.5. In the homeworks, sometimes you can't round, but in our situation, we could round. Okay, so let's go stat, go down to our calculators, we're on normal. Okay, so let's go, here we go, here's our normal right here. So we want to make our mean 28, and I want to make my standard deviation 1. I want to be less than or equal to, which I'm at less than, and I want to make this 25,000. Okay, so it's going to happen about 1.3% of the time. And this is how we denote it. I wish this thing wouldn't go away, but this is how we denote the notation. The probability that an x bar will be less than 25,000 equals 1. What percent was that again? 1.3%. Get back over there. 1.3%. Okay, so make sure you're comfortable working with those problems. Make sure you understand this concept right here. It's a huge concept. Okay, let's go to 7. Okay, so here's another one. Okay, this is another problem, so I'll do it real fast. So let's say a person uses 123 gallons of water daily. Assume the water is normally distribution. The population standard deviation is 21. Okay, now here they said normal, right? Population is normally distributed. That's good. Find the probability randomly one person will use more than 126. So I didn't take a sample, I'm just looking at one person, and it's a more than, so I'm looking for this. Okay, so this is the probability that any x will be greater than 126. So I pull out my StatCrunch. Let's go stat, calculators, normal. Okay, I want to pull my mean to be 1, 2, 3, standard deviation to be 21. I want to be greater than, just like I am there. These are my 126. 126. So it's going to be about 44.3%. 44.3%. And of course, you could write this as a decimal too. That's also. Okay, so now we're going to take what's the probability that the mean of a randomly selected sample of 15 people. A mean. So see, I'm not in x's anymore. I'm in x bars. These are all means now. 123, 126, but this is a mean. So I'm looking for the probability that the x bar will be greater than 126. Well, once I take a sample of so many people, once I take a sample of 15 people, my variability is going to go down. This thing's going to go down. The variability will go down because I expect most of my x bars to be closer to the mean. Okay, closer to the mean. So, but the concept's the same. Let's see if I got one up there. Okay, so now, okay, let me get rid of some of these. So now, I could cover this up for a sec. I need to figure out what these things are. So I'm at 123. Okay, this is the guy I need to figure out. Okay, so I have 21 divided by root 15. And you can round this. I know, like I said earlier, you can't do it in StackCrunch. So 5.422. Generally, I'll round to 3 digits. Okay, so now that's there. Now what I want to do is I want to find this shaded region to the right. Okay, so I need this thing to be 126. It's probably going to happen a lot less often. Oh, I'm greater than I need to be. Less. I'm less than I need to be greater than. So it's going to happen about 29% of the time. 29%. And I want to just shade that in so you know which way I was going. I was going this way. So the x bars are going to fall greater than 126 about 29% of the time. Okay? Alright, let's move on. A recent study of 75 workers found that 53 rode the bus daily. So here's your formula. If you choose to use your formula, this is called the second part over here, the z star times the square root of p hat 1 minus p hat over n. That's called your margin of error. Okay, that's called your margin of error, where the p hat is actually equal to x over n, where x is the number of successes. So I had 53 rode the bus out of 75, and I was interested. I'm trying to capture p. I'm trying to capture p, and p is the true percentage of workers who rode the bus. The true percent of workers who rode the bus. That's what I'm trying to capture. So I'm going to get it in an interval. Okay? So the way we do that, we go to our StackCrunch. Okay, for this case, it's going to be a little different. And we're going to go stat, and we're going to go to proportions. We're going to go to one sample, and I don't have data, I have summary. So now I come over here. I don't need that anymore. So the number of successes is the number of people who rode the bus. So throw that 53 in. The number of observations would be 75. We want to go to next. Don't hit calculate yet. We're not doing a hypothesis test, we're doing a confidence interval at 95% and calculate. And here's our answer right here. 60.4 and let's just say 81. So 60.4% and 81%. Okay? So it says, is it correct to say that half of the workers ride the bus to work each day? Okay, so what we have to do is look in our interval. We're looking for 50%. We're looking for 50%. Okay, is it correct to say? That would be a no. If 50% in there, if 50% was in there, we'd say yeah. We would say no. 50% is not in our interval. Okay, so you think more ride the bus or less ride the bus than 50%? And that would be more. Okay, it seems to me that more than 50%. 50% is not in our interval. Okay, that's 7.2. That's part of 7.2. Okay, so here's the second part of 7.2, and that's before we do studies, sometimes we like finding out the number of people we need to sample. Okay, we want to find out the number of people we need to sample. So this is all with the margin of error. So the margin of error is z star times the square root of some p hat, 1 minus p hat, over n. And this has to be less than or equal to some number. So I don't want this to go over that. Now these p hats, we don't know them because we haven't taken them. Okay, so we're just going to, we always assume the p hat equals 0.5. Most books call this p naught because it's not a p hat because we didn't actually take a p hat. Okay, so the formula when we solve for n, if you go through this whole mess and solve for n, it's going to be 0.25 divided by the error divided by the critical value squared. Okay, so here all I have to do is fill these things in. So E is going to be the error. That's within what percent? Within 0.5 accuracy. I'm at a 90% confidence interval, so you need to find the critical value for 90%. You have to be good at that. 1.645 squared. So now I just bring in my calculator and let's go ahead and run this. 0.25 divided by, open parentheses, let's close it, let's square the numerator or the denominator, and let's see this. So we're going to need, and you always round up, so this came out to be 270, so we need to go up to 271. So if we take 271 people, if we take at least that 271 people, we're guaranteed to have 5%. The more you go up, the less this number goes down. Okay, so be comfortable doing that. Okay, so I had this data in here and it disappeared from my StatCrunch. So all I'm going to say is the point estimate, this one's really easy, I don't want to spend too much time. The point estimate for, find the point estimate for mean length of all. Once they say all, the point estimate, okay, point estimate estimates, I know that sounds funny, estimates you. This is you. That's you. But the point estimate, what can we use to estimate mu? We've talked about this earlier. We could use x bar. So all you have to do is find the average of these numbers. So put these in a list. I had put them in a list already. They disappeared on me. Okay, put these numbers in a list, and then you do stat, summary stats, columns. And then there'll be an area for you to find the mean. Okay, or the mean may just be given to you. Okay, so let's move on here. And okay, so whenever we did these problems in the homework, there was an option. They either gave us data. Very few of them gave us data. Most gave us a summary. Most of them. So in this case, they're giving us the data. So we have to interpret 95% confidence interval for all U.S. millionaires. Assume that ages are normally distributed and standard deviation is 13 years. Okay, so this is what this actually means. So we're finding this p hat, and we're going to be going 1.96 standard deviations this way and negative 1 standard deviations this way. So all this stuff is in your StatCrunch. We can do it on StatCrunch, but we're talking about means here, so the formula changes a little bit. It's the x bar now because I'm trying to estimate this mu. I'm trying to capture this guy. So it's x bar equals this z star. And the reason that I know this z star is because this is known. You have to know that concept. This mu is known, so you're going to use a z. And it's going to, if this is known, then I know that. So it's going to be that over the square root of n. Remember this thing right here? These aren't p hats, sorry. These are x bars. See this here? That's the standard deviation. That's how much they vary back and forth. So anyways, to do this problem, if they give you data, we just go to our StatCrunch. Okay, now this is going to be a z statistic. We're doing a z. So we want to go to z statistics, one sample. They gave us data here, so click data. There was a homework problem like this. What variable one is there? Okay, standard deviation is optional, but we know it. The standard deviation, okay, standard deviation is 13. They give it to us. Okay, there's nothing else there. We want to do a confidence interval. We want 95%. Let's go ahead and calculate. There you go, that's our interval. 54.45 and 62.94. Okay, so these are your intervals right here. Okay, 54.45 and where'd that little guy go? 62.94. So we are 95% confident. Okay. The mean age. This is the mean age. Okay. Or this is we're confident that the mean age is in here somewhere. All right, let's move on. Okay, so you know we have to do these backwards problems here too. So just like before, we use this z star times this over the square root of n. This has to be less than some error, this certain error range. So solving for n, we're going to get this. Okay, it's very similar to what we did before. Okay, so in this case, we want to know how many should we sample, how large of a sample to be accurate within 200, to be within $200. So whatever my final interval is, it should be within $200. So this here is 200. Okay, so let's go ahead and run these numbers over here. I'll just put an arrow here. This is 200. So what I need to do is the standard deviation is 1050. So I need to square that, divided by, E is going to be my 200, divided by the about 95%, so it's 1.96, and I square it. Okay, so this is going to give me the answer. That's it. So 10050 squared. I'm going to divide that, open my parentheses. You need to come up with a way that you're good at using your calculator. Take a peek to make sure I'm still good. Square the bottom. So we need to take 106 people. So we want to take, so n needs to be greater than that. So we would take at least 106. Okay, so let's move on. The next one's about t's. This is when our standard deviation is not known. So this is unknown. Okay, so and also we have to be comfortable with this thing called the central limit theorem. The central limit theorem says n has to be 30 for the distribution of x bars, or not ps, for x bars, for the distribution of x bars to be normal. Okay, so n has to be 30 or more. So for example, we'll do these things here. Find the t-score with a sample size of 20 that has a 0.95 between them. So I'm not in z's anymore, I'm on t's. So you need to find the t-scores. So you need to find this t, and you need to find this t. Okay, for a sample size of 20, so the degree of freedom is going to be 19. and this middle is 95%. So if this middle is 95%, then that means this is 5%. I'm sorry, that's 2.5%. The one-tailed probabilities are going to be 2.5%, and this one probability is going to be 2.5%. So what we want to do is pull our StatCrunch. We go Stat, Calc. I want to go to T now. I'm not in Z's, I'm in T's. Okay, you're a T calculator. You see these curves will change. These curves will change. If you look at the Z's, they'll always look the same. Okay, so I need a degree of freedom of 19. In this right, I could do right or left. This needs to be 2.5.025. Compute. So it's 2.09. So this is 2.09. This is going to be negative 2.09. Okay? And I'll just prove that to you. So what happens here is I'm right here. This is 95. So that's this is 2.5 to the right. So now I could just do 2.5 to the left. Okay, hopefully everybody's with me. So it's the same thing, but it's just negative. So that's the answer to the first one. Okay, so now let's say this. Choose whether to use a TZ, or neither. Okay, so I'm doing the second portion. You have to be good at this. This is going to be on there. Okay, so if you take 50 people, so automatically n is greater than 50. Okay, so this is a good thing. Okay, but they tell you the population is approximately normal. Okay, the only time you have to use the CLT, is if the original distribution, if the population distribution is skewed. That's the only time you have to use the CLT. Okay, so since the population distribution is approximately normal, okay, I don't have to use this. Okay, the X bars will be normal. Now I'm looking for this. The standard deviation is known. The population standard deviation is known. So that's this guy right here. Okay, so we're going to use a Z. Number 2. A random size 20, okay, and a population approximately normal. So they give us that as normal, so I don't need the central limit there. Because see, this is less than 30, so I would need it. But since this is normal, I don't need it. The X bars will be normal. But the standard deviation is unknown. The standard deviation is unknown. So since it's unknown, we use T's. Number 3, 13, in which the population is left skewed. So now the population is skewed. So now we need to use the central limit theorem. Okay, and is this greater than 30? No. So this would be neither. Okay, so make sure you're comfortable with that. Watch this a few times and listen to what I said. If the pop is normal, then we could have any size n. Pop is normal, we could use any size n. If this is known, we use Z's. If that is unknown, we use T's. If the pop is skewed, we need 30 or more. If you have 30 or more, then we're good to go. Okay? If n is less than 30, we can't proceed. We cannot proceed. If n is 30, we can proceed. And just do the same stuff. Okay, so let's do the last one. This is a 90% confidence interval, so it's very similar to the formula before, but instead of the Z's, I'm going to be using the T's. And instead of sigma, I'm going to be using S because sigma is unknown. Okay, so 49 shoppers, their average of the 49 was 23.45. Okay, and the standard deviation from the shoppers was $2.80, and find a 90%. So 90% is going to give me a critical value of 1.645. So you could just plug all these numbers in. Okay, first of all, we don't have a z. That's my fault. Okay, let's backtrack. We're not using t. We're not using z's. We're using t's. So t star for a 90% is going to be a little different. Okay, now you could just run all this stuff on StatCrunch and you don't have to worry, but for anybody that's interested, I'm just going to find this critical value. Okay, so you go stat, calculator, t. I took 49 people, so my degree of freedom is 48. The degree of freedom is always one less. If the middle is 90%, then the right tail is 5%. Hope you could see that. So it's 1.67. Okay, 1.67, 1.677. Do you see that? If this is the middle is 95, the middle is 90, what's the right hand? What's the left and the right? 5%, 5%. So this critical T, all you do is do this. 5%, degree of freedom 48, because every T is different. Okay, so basically we're going to be using StatCrunch for this though. Okay, but it's a T, so it's a T statistic. One sample, they gave me a summary. The sample mean was 23.45. The sample standard deviation is $2.80. The sample size was 49. They need that. Let's go next. Confidence interval, I think they said 90. 90. Next. And calculate. So the answer to this would be 22.78, 22.78, and that's going to go all the way into 24.12. And I'm actually 90% confident that we're capturing that this interval captures the mean amount, which would be mu. I mean that which is the true mean amount of money spent is in our interval. Okay, so that's it. I'm going to stop it now because of time. It's just really long and don't want to bore you too much. Or maybe you love this stuff. Hopefully the latter, or however they say it. Alright, so thank you so much and good luck on Monday or Wednesday.